start. How are you guys doing? Having fun? Enjoying the class? I see a reasonable number of people smiling at me. Otherwise, you won't be here. So, do you remember the prediction made in our first class? One of them is the distance you are to the front. That is inversely proportional to your performance on average in the class. Not really very. Second is the number of people in this classroom is inversely proportional to the temperature outside. One is today. I was wondering how many people will show up. Today is our first day, so it's very nice today. It's very warm outside. But let me repeat what I said in the beginning. And pass the word to your friends who are not here. Since you are here working, I want to say that. Ever since your friend this is recording, so that I listen my voice there. You got it. If you can come to class, do so because it's essential for you to make your progress. If you don't show up, not doing very well, that's a problem. And our first exam is coming in about 2 weeks. So if you look at our schedule, so we made a little bit change here. So I'm going to give next 3 lectures today, next Monday and Wednesday. Then Dr. Winslow will return to give 2 more lectures. And we have to shift it because of some conflicts. And I hope you understand. So the first exam, I believe is March 2nd. It's on a Monday. And on that day, we'll still have the lecture at the same time. And the exam is in the evening, 2 hours. And then for the second lecture, right now the schedule says we're going to have a lecture on the day, so but we'll probably have to cancel that lecture. The second exam, on the exam day, we're not going to have a lecture. But the first exam day, we still have it because we have line up more than the first exam. Just to let you know. So we might periodically make small changes to our course schedule, so here we'll post this. So today what I will do is that I will continue to finish half of the lecture 2 handout I gave a couple of weeks ago that I didn't have time to finish. But that's very important. But before I continue, I'm going to ask you. So I gave a first homework assignment about 2 weeks ago. How do you guys feel? Was that useful? Hard? Far? Did you learn something from that? Yes? If you learn something from that, I think that would be useful. I thought it was useful for exercise. But if you have suggestions how to make that even more fun, more useful, let us know. Because that is meant for you to exercise your knowledge, your calculation functions, and do a little experiment on your own. So I hope you have learned something. So I have posted my second homework today, which should be posted on Blackboard by noon today. Not a direct concern what we'll be discussing today. It's also a very important problem. As you see by now, the homework we're giving you are meant to complement or reinforce what you're supposed to learn in a class. Now, what we're talking about today, and last time I rushed to this point, there are a couple of slides before this. About the split field that believe by carbon, and this is where I stopped last time. This is a very important topic that is concerned how you analyze your signal. By now, you have a general idea. Like if you look inside our brain, your brain, my brain, animal's brain, for many species, there are neural signals that convey information about what we feel, perceive from outside, what we see by eyes, feel by fingertip, hear by our ear, all of them. And those signals we call action potentials. And or for short, people call spike. Spike action potential is the same thing. Action potential is more formal name. Spikes, whatever researchers use it. So indicators, literatures, 90% of the time people just call it spike because it looks like spike. And next week, and then we will undergraduate for the class. And I'll take all of you through a live conduction velocity next Thursday and Friday. And that is also directly linked to this. I'll explain it. So here in the brain, everything is very obvious. Okay, so where did action potential come from? So essentially, before you understand everything on the rest of the class, we talk about how the brain controls this and that. You really need to know what is behind these action potentials. So for today's lecture, I will take you to basic methods to quantitatively analyze this. Right? So remember, you are biomedical engineers. You are learning biology, but the difference between you and a biology student, whenever you say biology phenomenon, you immediately should come up with the question, how do I quantify? Quantification is everything we do as engineers. On top of biology, this is what we're going to talk about. And since you have learned a month or so and other class before this, so you should know enough about basic biology of action potential, ion channels, all of that. So I'm going to talk about it. We'll talk about once you have action potential, how would you analyze it quantitatively, mathematically? Okay. Now before that, I'm just quickly to define a couple of things. If you look at the neuron in the brain, there are many. So let's take one typical neuron called a primary cell. It has a cell body. It has dendrites, it has axons. You will know dendrites is where impulse from our neurons contact. And cell body is where finally information is processed, and action potential is generated, and axon is the output cable in your neuron. Okay. So before we talk about action potential, you should also know how would scientists measure action potential. This is not something you can look at your eye. You measure by microelectrode. A couple of weeks ago, you heard a lecture by one of the researchers in my lab, Dr. Shinzo, talk about optical imaging. That's another way to measure action potential. This is something really new. That's why I asked him to give you. He's one of the best researchers in this area now. So to talk to you how to measure. But today we're going to talk about much more conventional, traditional. That's measured by electrodes. Because the optical signal we measure on our brain is still based on electrical signal. The basis is this here we want to measure. So if you draw the electrical signal here, because you know now within the cell body, there's a voltage difference between inside and outside. You learn all of this prior to the class. So if you drop an electrode right next to the cell body, outside the cell body, outside, and you will be able to pick up the potential changes in action potential in general. Okay? And that is in here. So that's called an extracellular recording. So you basically record the potential changes in the nearby cell body that will action potential generate. You'll pick up some signals. Reference is graph. Okay. Now, if you want to take an even finer version, then you can take the sharper electrode, penetrate the cell memory, and record from inside. Now you're inside the cell in an intracellular space. That is called intracellular recording, and this is an example. Now here you can see the change of the transmembrane potential. You should be familiar with. On top of that, action potential. So we call it intracellular recording. And then here we can say EPSP, IPSP, and spike. For extracellular recording, you can only say spike. Okay. Now, in the literature, if you read it, 90% of the time, maybe 95% of the time, people, researchers apply extracellular recording. Why? Why don't they all do intracellular recording? Intracellular recording can be both back and this. Because this is very hard. Okay. The cell body is in the order of 20 to 30 micron, and brain has pulsation. This is like you take something. Let's say you take a hook. You're gonna. I mean, I don't know if any of you come from. This is winter now. I don't know if any of you come from northern state, like Minnesota. If you do, you know there's something called an ice fish. You go to the lake, it's frozen, you drill a hole, and there are fishes somewhere down water. Then you take a droplet, hook into there. Somewhere down that, you hook, there's a fish that will bite, or you lower your fish enough to your hook to go there. That's just like very important. You don't see it, you drop your electrode. Now, if that fish is moving, if the whole water is moving, fish is tagging, this is your hook. And how do you get out? This is what we intracellular recording. Intracellular recording is extremely difficult. It's order of magnitude more difficult than extracellular recording. And so that's why most of data you read from literature from this textbook comes from extracellular recording. But you want to know that's the difference. Now another terminology you should know is that is what we call wave orientation. So depends on how we record that signal. Now quite often, researchers can record the neurons' action potential spikes from an intact neuron. In that case, we call this in vivo recording. But you can also take a brain tissue, put slices, or isolate neuron in the nutrition liquid. Then you can also record in vitro. So those are basic terminology we're working on. Now from here forward, I'm going to just concentrate on spikes. And then that's essentially basically a coding element of the brain. Okay. If you finish this class, you don't know what a spike is. You're really missing the key concept. Okay. This is very important. This is the foundation of our brain. It's like you look at a building, and each brick of this building, which is made of the brain. That's this brain. Yes.
For the cell body to do cellular reports, what is the baseline?
This one?
Yeah.
Baseline changes because that's transmemory potential change. Remember, for action potential to generate, you need influx ions into the membrane, and the membrane becomes depolarized. Once it depolarizes to pass the threshold, then you generate this action potential and come back and hyperpolarize yourself. And you observe this if you have electric inside the Okay, so to move on from here. So that's the textbook picture I showed you. So real spike looks like. And unfortunately, the lab we're going to do today next year, you will not be able to see real spike. Because what we're going to measure is called a compound action potential. The real spike measurement is actually pretty challenging. But if any of you want to see a real spike from a real brain, just come to the lab. We record this every day. So here is an example we're showing you. A trace of a real spike recorded from a monocytic brain cell cortex. So if you send a signal through a speakerphone, which we listen all the time, you will hear something like pop, 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 pop. It's like a Morse code. Really, you listen to this. It's a lot of niches in the brain. When I was an engineer student, 30 years ago, I heard this. I think it's really fascinating. This is how the brain communicate between neuron and neuron, right? So essentially, now you understand why we should call it spike. It is just a spike. And there's action potential in response to this. So that's what it's like if you have electrical activation. So today, what we're going to consider is that how now, if I give you the signal, how you quantify this? Because what are that spike showing? A sequence of spike, individual called a spike, a sequence of when people use called spike trend, or sequence of action potential. Spike trend is what it refers to. Okay. But in order to get that spike, to analyze it, and we start with signal like this. If we're talking about brain size, it's like an ocean. It's a lot of waves going on. Okay. So you will pick up something like this. This is all raw data. What is this? And if you heard the term of EEG, this is what it is. So in your brain, there are many neurons that are going on off all the time. So if you drop the electrode somewhere, you pick up a slow wave of that thing. Then the neuron very next to your electrode give you that spike. The rest of the spike you don't see. They all contribute to slow wave. Okay. Now, once you take this signal, of course, this is a low frequency. You can do a high pass filter, and you get rid of this, you get something like this. Each of these, you take this, expand that, just look at this, right? This is formula, should be familiar with so far. Now, if you look at action potential have a properties. What is the number one property that is coming to your mind when it's come to action potential?
All or none.
Yes, it's all or none. So action potential, either you have it or don't have it. Okay. You don't have half. So since you have all or none, the shape and height of this really doesn't matter. What matters is what? It's when it occurs. It's time. So from here, we can measure time of action potential. Let's say we pick a peak time. We denote this just by one line. We can denote by one dot. So this whole chain of action potential now can be represented at this time. This is what we call spectrum. So only time matters. So once you record action potential, you got a time for each spike. Only that spike matters. And this, it turns out, it is equivalent to a discrete statistical process. Now this is where we introduce mathematics now. Okay, it's action potential. Okay. So there are generally there are four ways to quantify action potential. I'm going to walk you through. This is the four things we're going to walk through, and I'll finish this series of slides with this slides again. Okay. Once for the mean firing rate and the post-stimulus histogram, period histogram, histogram, each move with increasing complexity and then more information. So we're going to walk through one by one. All of those four methods, quantification methods, are commonly used in the literature. If you understand this, you can read 80 to 90% of the neuroscience literature to describe every process. Okay. So let's start with this. Mean firing rate. What is mean firing rate? Mean firing rate is a measurement of number of spikes per unit time. Okay. Very straightforward. So if you look at the unit here, it's spike per second. Okay. So you pick up time window. For example, in this case, this is an example of visual cortex. Researchers recording neurons when you give these light bars with different orientations. It's like you give this way, this direction. Okay. And later on, you will hear from Dr. Connor. He comes to talk about visual system, how important biology. So I'll just say, if you have this kind of data in this orientation works, those spikes in this orientation, a lot of spikes. In this orientation, a few spikes. But how do I quantify this? So if you measure how many spikes per this time, you convert that spike per second, and you can plot a curve of this. This y-axis is the mean firing rate. Mean firing rate or average spikes rate simply. Okay. And this is orientation in angle degree. The 0 is what we refer to as here. So we can say this neuron responds most to this 0 degree and this. So this firing rate is computed by this much. Number of spikes within time window divided by this number. Very straightforward. So I'm going to ask you to exercise this in your homework and in your exam. This is the basic thing. It's very simple, but you'll be surprised if you don't do one few times by your hand. You'll be stuck somewhere. But of course, when researchers do this kind of measurement, and the neuron in the brain is very stochastic, right? So when this is the one time they do this. Now, if you do this 10 times, every time is different. This is what we'll get into in the next couple of slides. So you need to take the accurate measurement. Researchers use repeat something many times. For example, for this orientation, once, twice, 10 times, 50 times, 100 times. Okay. then you have all of the data. Then this formula would be, if you do n trial 10 times, the mean firing rate would be number of spikes within time window from n trials, divided the length of time window and divided by n. Okay. Then you got firing rate. This is basically very basic. Okay. So let's then give you another example. So now let's say take an example. This is actually an example from frog the nerve that connect to frog the ear. So if you record from that nerve, then you place time for 500 milliseconds. Place time. Some lasts half a second. So what you can see here, you place once. Now each dot is spiked. Now we use each dot for spike because the timing matters. One plotted line, it's just for easier for you to see. So essentially, it's not. Okay. You do so. What if this experiment was that it is once, twice, you repeat many times. So the y-axis now is the repetition time, trial time. So there are 50 times. Okay, 50 times. And if I plot this way, every spike that are recorded when did 50 times, placed on 50 times, recorded here. And first of all, this part is called the dot raster. Just terminology, just dot raster. Okay. But what you notice problem here is that there are a lot more spikes. The first one, there's a delay, right? In every place, you don't get spike. There's this delay here. But you really got a spike here. It's about how many? 20 milliseconds. It's milliseconds. You've got a lot of spike here because you can see it just by your eye, right? And then as time goes by, this thing goes slow. Now, if I give the data to you, I will. Okay. And if I give you all data to you, say, compute mean firing rate. So use the formula we just talked last time. Your computer in a couple seconds. 30 seconds, you can fire rate. So fire rate of this, that you count all spikes with the time window divided by time window divided by number of trial, which is 50. You get it, let's say, let me count 20 spikes per second. So that tells you within this half second, this neuron on average will file 20 spikes per second. If you got another neuron, that number becomes 40. then you know that neuron fire twice as more. However, this number alone does not tell you the fact that this neuron actually within a half second, it does not fire 20 spikes per second every moment. It fires more beginning, less and less space. That is a common property of all neurons. We call it adaptation. Adaptation. This is actually general property. So then how do you quantify that adaptation? So fire rate alone does not quantify. Now you need something else. This is why we introduce the next measure. The next measure called post-student histogram. Here's how we measure. Given this stop loss strip, then we divide this time axis by many beats. Let's say we divide every 10 milliseconds a beat. Then within that 10 milliseconds, we calculate fire rate. Okay? Then we come up with this plot. Now this is fire rate, this time. You can see there's almost no spikes for first about 10 milliseconds. And about this time, for 20 milliseconds, a lot of spikes, about 250 spikes per second. And then it goes down like this. Okay? This is called post-student histogram. So what does it tell you? This tells you something we refer to as a temporal pattern. Temporal pattern. So now this can quantify how this neuron fires as a function of time. So in general, the neuron firing can be quantified either by discharge rate or mean fire rate or temporal discharge patterns. Of course, once you have this, you can go back and compute the discharge rate, but not fire rate. So that's the second measure. Yes?
Just to clarify for the dot raster,
Yeah.
does each row correspond to a single neuron in a single trial?
Yes. Yeah. This is same neuron. Each row corresponds to one child, and the next child. All of this comes from a single row. Good. Any questions? Yes.
And for the histogram, you just like bin that whole the dot raster. And just
Yes.
slide it
Yeah.
over. Okay, gotcha.
So this is a very basic, but let me trust me. I'm gonna ask you to do this by your hand. So the base what you do is the following, right? You got a dot raster like this. You got a dot here, not here. You know, once you understand the concept, it's very straightforward. And when you do fire rate, you take the whole duration, take it, right? But here, what's different now is that you don't do this with beans. So you bean this. Now, of course, how big is the bean, you can decide. And then what you do is you look at it within this bean, within each bean. Within this bean, how many spikes? You compute the mean fire rate here. You look at second bean, how many spikes? Compute mean fire rate. Look at third bean, how many spikes? So once we compute this, essentially, you compute the mean fire rate at each bean now instead of the whole thing. That's all. The same thing. Okay? So that gives you this. This is actually quite useful. Very commonly used. Now, but let's move on. So for this neuron, if you can compute this, then you can compute the mean fire rate. But there are times the neurons have more interesting things over time, not just decay. Right? For example, if you look at neuron in auditory system, you play tone. Tone, if you listen to what if I synthesize a very pure tone, it's periodic. So it turns out we'll expand this a little bit more in the next week. But some neurons, particularly in auditory system, will follow this. So there's a periodic signals. It's not just decay. They'll go up and down as tone goes up, right? It's a sinusoid. So how to quantify that? So here's the example. So if you record, this is recording from a cat audio recording by a professor in this department many years ago. And now if you play a tone, for example, this is actually a graph from the real paper, so these are real data. This is audio illustration. So for example, they place a tone about 668 hertz. Okay. So they play tone for one part, the second time, so this is part right? Every part is this. Now if you take this part, expand this is that tone. Manicured. Now there's a slide here. Up here it looks like they're periodic, but how to quantify? So this is how to quantify this. So they took about 5 periods. 1, 2, 3, 4. I think 6 periods here. Okay. And now it can be any number of recurrence. If you just take one period, you cannot say repeat. You can take two, you say repeat. Usually it takes a couple. And in this case, it's a little bit arbitrary. But it's 6 periods. And then they found these spikes, and then using the same method we said earlier, turn it into dots. Then on the next 6 periods, another one, another one. So essentially, they create a dot raster. But now line up by period, multiple integers of period. Then they apply the same methods we just talked about, the computed period data, post-distributed histogram. Then they computed this, they got this. But because this is line up by multiple integers, it's number of periods, so we call this period histogram. But essentially, computed the same way as post-distributed histogram, except that where the line up is 0 is the beginning of period instead of beginning of post-students. Okay. If they line up every one of them at the beginning of the students, they will have computed post-students here, histogram. Okay. But once the computer here, and what you can see here now, this neurofiring goes up and down, the side stays here. If you measure the distance between two peaks, it's 1.3 milliseconds. So you do a little calculation, that's exactly the distance between sinusoid. So this histogram now, period histogram, tell you this neuron actually follow the sinusoidal pure tones precisely. And then later on, next week, we'll talk about in which cases neuron does not follow. The term be very important. Now we won't talk about quantification. So by calculating period histogram, then you can determine this neuron has this time following response. I'll give you another one you may not have. But here's one step further. So I just shown you that I say, okay, there's a period here. Now you could now push me and say, well, how do you know this is really following? I mean, this is a pretty clear case, right? If I give you a case where after all the calculation, you are getting something like is there following? Now, of course, I'll give you another case. After calculation, first there's not. Well, maybe, right? Now we see. Now we need another level of calculation. So I'm walking you basically. I'm dragging you further down to the water. Okay. So how do you quantify this? So I give you this. How do I quantify it? Saying that there is a significant quantity. Now, before that, I will give you another example. So this example is from a sensory system. Okay. If I get your finger here, and I tap on your finger with computer-controlled probe, that basically gives sinusoidal indentation here, and record from here. Then what you do here, that's sinusoidal indentation into your skin. Then you can spike it like this. Okay. Now, you can calculate period histogram, and this is what you do. But you can also calculate something called an interspike interval histogram. That is, you have all the spikes. Now I calculate the interval between two spikes. Right? Just like in that other example, I said, you have spike, you from the number one spike, first, second, and third, all the way to the nth spike. If you look at the interval, time interval between first and second, that's one interval. Between second and third, it's 9 interval. If you compute all the intervals for n spikes, you will have n-1 intervals. Then you make a histogram of that. That's shown somewhere here. That's called interspike interval histogram. So let me draw a little bit to tell you how you do this. So it's just like if this is a one spike trend, between first and the second spike, you will have interval. Between second and third, you have another interval. If we call it tau 1, tau 2, this will be tau 3. If this is the nth spike, this n-minus spike, then you have n tau n-1. So you have n-1 time component. How do you make histogram? So you make a histogram for this tau. Now, if the tau 1, let's say, let's make it up. This is a 10 milliseconds. This is 5 milliseconds. This is 0. Okay. If tau 1 is, let's say, 3 milliseconds, you essentially have so far so on. Eventually, you create a histogram that told you basically how many tiles you have. How many tiles? Something like you can create a histogram. That is histogram here. Now, just quickly, so if a spike that's a mean firing rate is 20 spikes per second, what is the average interval? 20 spikes per second. What is the average tau? Just guess. What's that, Honey? It's 1 over that. Right? So you can have. So now you see this interval is actually directly linked to it. So if a spike fire completely periodically, that you have spike is every cycle, then that's very simple. The tau and the average spike interval is mathematically big. But most neurons fire perfectly. So there's a reason to construct an interface. I say some of you have looks puzzled by it, but let me go through here. We may have to make interspike interval histogram is the last one. Is 4 things. Right? We'll talk about 4 things: mean fire rate, post-stimulus histogram, period histogram, interspike interval histogram. Interspike interval histogram capture everything. And you can go back to reverse engineer everything. But if you require more information, and to capture it. Okay. So now, let me also just give you an example with the data here. So for these neurons that fire always you see line up here. Now the reason this post-stimulus interval histogram is only have one peak is that because you only capture one period. If you capture the second period, you have another peak, another peak, just like what we did before. Okay, but this interval histogram, you look here, it has 2 peaks here. One of them around 100 milliseconds. What does that mean? Why this data has a peak at 100 milliseconds? 100 milliseconds. What is the period of? It's 10 hertz, right? That's because this sinusoid is 10 hertz. So you have every 10 hertz, say you one. So those spike intervals give you this, or one of these, like 2, 3, 4 milliseconds. Why do you have that? So if a neuron fire perfectly at 10 hertz, every period fire once, what is the interval histogram you have? You should have only one peak, exactly at 100 milliseconds, right? Is this clear? So if I have a hypothetical neuron, I give a 10 hertz stimulation, the neuron only fire every time there's a peak in the sinusoid, perfectly. The interval histogram should give you one peak, exactly, with the repetition. Really, 100 hertz. But as you see here, which is naturally, whenever neuron fire, neuron does not just fire one spike. It comes 2, 3 spikes together. 2, 3 spikes. Then 100 milliseconds later, 2, 3 spikes, 2, 3 spikes, 2, 3 spikes. Right? This is a big interval. It's captured by 100 milliseconds. But these 2, 3 spikes together, their interval is very short. That's why you have these. We'll come back and revisit this. Okay. It's a little bit very puzzle now. I just want to throw it there, why is data? Okay. So let's continue. So we'll continue to talk about how do you quantify a period histogram. So how do you know statistically the neuron is firing following the sinusoid in a significant way? And this is, it turns out, you can use a statistic called circular motion. Okay. It's illustrated here, and it's also used as well. So when you go from 0 to pi, that is the one cycle of the sinusoid. It's like you circle here. So that's mathematics we introduce it. So I'm going to put mathematics here, tell you how to compute this, then you can have some time to work on this yourself. So to quantify periodicity in an interval here, and here's what I do. There are 2 methods. And that property that the neuron fires discharges following period, we also call it physiological. Put it in the word here. So this is called physiological. This is exactly engineering term. If you have to learn linear system, you give impulse, give output. If input is sinusoidal, output is sinusoidal, that locks with this. It's called physiological. How to quantify physiological? There are 2 ways to quantify physiological. One of them is that if you know time of each spike, and you can plug this, there's something called a vector strip, using basically the mathematics of a circular statistics in the previous slide. You can do this by hand. So if I give you n number of spike time, I say calculate vector strength. You should be able to do it by hand, perhaps with a calculator. Another way, easier way to do it, if you have a MATLAB, since computer is available, MATLAB is everywhere now. This computer, this one, is that you compute the power spectrum of this, and you compute something called synchronization index. It's just taking that signal. If you compute the power spectrum of that, and you know if it's a periodic, you have a peak, it's not frequency. Compute that, normalize this one. Okay. So this is something we're going to get you exercise. There's two ways you can quantify periodicity. Now, then we do now final quantified mathematics we're going to talk about in this one now is that if I give you general spectrum, very general. Now I'm not assuming any periodicity. What is mathematics uses? This is the core of this lecture. I think you'll be overlapping right now. So now let's go back to look at the spectrum. This is spectrum. First spike, second, and third. And the time distance between the two spikes, we'll call it tau. Okay. And how many of you, I think most of you should have learned, have taken the probability now, right? Have you heard about Poisson process? Yes. So in the probability course, Poisson process you heard is probably in this form. So this is spectrum, but if you plot here the number of spikes within time window, so here until this point is 0, and then now you have 1, then you have 1 until here is 2. That's Poisson process. Most likely, if I have not looked at your textbook, this is part Poisson process you learn. But it's the same Poisson process can be mathematically expressed as this, called arrival time. Usually they talk about this in stochastic process. Did you guys learn this in Poisson process? Did you learn what? Both? Have you learned both? Both expression in Poisson process? They both are mathematically equivalent. Right? So what do you like to learn when you hear Poisson process the last time? Is that they use the mathematical process will not give you spikes. They give you arrival time of bus. You sit in the bus station, there's a bus, then X, minutes later, there's another bus, right? That's use the arrival time, they told you. Okay. But what I'm going to do is that it turns out spectrum is perfectly modeled by Poisson process, but most conveniently in this form. But these two forms, in which in a moment I'll show you mathematical format, they're equivalent. I just want to emphasize. Either you count number of spikes with a given time, which will give you a counting process, or describe every spike time, arrival time. They are mathematically equivalent. Okay? So if you look at math behind this, the probability of n spikes within n of t time is this. There's lambda. That's what you should have learned now. I'm almost sure this is what they taught in the mathematics probability course. But then, so that's the formula that describes this. But if you choose to use this format, which turns to be much easier to work with spike data, then you have this. What it describes this now is this tau intervals. The interspike interval I side, it satisfies this exponential distribution here. But why this is easier to work with? Because you see, if you have a spike, as long as you know interspike interval and the first time of first spike, you can construct everything, right? You gave that's what is the homework assignment today is about, and ask you to exercise this. If you know the 0 for first spike time, then you know every tau 1, tau 2, all the way to tau n. Then you can construct the whole thing. So all you need to describe this is the distribution of tau, which in the Poisson process, we call it, strictly speaking, it's a homogeneous process. You learn in the probability class. This tau satisfies the Poisson distribution, exponential distribution, like this one. Now, sadly, none of the neuron is perfect like this. So I shall give you a perfect neuron. It's like this, mathematical neuron. Then I'm going to walk through an imperfect neuron, a real neuron, and how we model this. That's where I will end this lecture. Once I have this, if you plot on the exponential distribution, it's like this. Okay, this is interspike interval. Can you use this to model real neuron? This is the Poisson process. This means interval distribution satisfy this density function. This is what we define. Can we use this model earlier on given knowledge we have? If we can't, why? Can you? So let me give you push you a little bit one step further. So if this is what I described earlier on, how close to spike can be? That means how small a interval, how is distance between two spikes, right? If this is distribution, how small that tau is?
So this distribution is then supposed to be arbitrarily small.
Arbitrarily small.
And small there, the more likely it is.
Right. Does that make sense biologically?
No.
Why?
That's just way too frequent.
Yeah, but there's a reason biologically. You cannot have arbitrarily small refraction. Yes, refraction too. Perfect. Yeah. Because that's the second property of spike. Actually, we set up all along. Now we're involved in the second property of spike. And that is spike has this something called Euler refractory period. That is after you have one neuron generate one spike, you cannot generate a spike immediately. It has to delay a little bit. And in fact, as we're going to talk about next week in the lab, there's two periods. There's something called relative, absolute and relative, right? Because you cannot have two spikes absolutely close. This does not work. This cannot fit around. How we do? Well, I can introduce refractory period. For example, if that's interval histogram, if I introduce histogram like this, you say, yeah, you can have almost no spike at the beginning and gradually have more spike at the end here. That modus match the two refractory period. So now, this is a function distribution called a gamma function. Okay, but gamma function is no longer Poisson process. Okay, now we're deviated from Poisson process. Okay, then how do we link this to data now? This is mathematics. How do we link the data? So if I give you real spectrum and ask you to calculate histogram, which you will do in the homework assignment today, you have something like this, right? Very much like this. You will see by your eye that the spectrum I give it to you. It's not like this. It's not like Poisson. You have this gap here. That's because of refractory period. Okay. You have this, then you can have a function, gamma function. You can have a curve fit on this. So, and the reason we go through here is that, so the reason we do this is to give you a way to model mathematics. So let me go all the way back until why we're watching. So when you study spikes biologically, you have a neuron, you drop your electrode, you record all the spike. You can do all the measurement I just told you. Mean fire rate, post-limit histogram, period histogram, blah, blah, blah. Okay. If you're a biologist, this is where you start. This is good enough. I want to quantify it. In fact, you're better than average biologist. I quantify all of them. But if you're engineers, we take one step further. And first one, we quantify it. Second one, we want to model it. Model by means we want to build a mathematical model to describe this. Why you want to do this? This is not just for pure exercise. Now, somewhere down the road in the class, you're here. Suppose some of you probably interested. Suppose you want to build a robot. A robot that will control my arm almost the same way my arm moves naturally. But what controls my arm? And what controls my arm is the nerves running here all the way to the brain. You're here. Now, how does the brain control my arm? Brain sends all the action potentials here. Okay. So if you know all the action potentials running down here, when I do this action or that action, you essentially can control my arm. But how do you do this? Well, you're going to put an electrode in my brain, asking me to do this, and record all the spike. But what if you want to do this 100, 1,000, 10,000 times another time? You cannot go there to record spike all the time. It's not economical. What do? Well, I do once or 10 times. I use the mathematics we talk about now. I build a mathematical model. Now I have a mathematical model. Next time you say, give me spike to do this or to do that. I just use my model to generate. This is why we go exercise. From the data to quantification to the model. If you can model a neuron spectrum accurately, you don't need an experiment anymore. This is my neuron. This is my mathematical model. Whenever you want to do this and that, I just generate it. Okay, that's called modeling and simulation. That's what I want you to do. I just want to why we are not wasting our time to do this. Okay? So how do we model this? So The way to model is funny. Suppose this is the interval distribution of a real neuron. Now I'm going to say, here's a real neuron. Data, model one. Build a model for me so you can generate these neural spikes statistically, accurately, whenever I want, however long you want. So what you do is you want to generate a distribution. Okay? This is something that is good. So the way to generate distribution, like Poisson distribution or gamma distribution, is by starting with uniform distribution. This is a very useful skill. So you want a Gaussian random variable, this is a random variable. If I say, generate Gaussian random for me, or generate Poisson process for me, or you could method like typing Poisson X bar. That's cheating. That's cheating. But there's actually a very beautiful mathematics saying that if you start from uniform distribution, what a uniform distribution is that it's between 0 and 1, that is equal in probability. If you start from here, you can produce any distribution. I don't know if you guys have learned that yet, but this is what it's saying. Okay? If U is a random variable of a uniform distribution between 0 and 1, and then f of t is a probability distribution function of a random variable tau, then the inverse function here is a random variable with a probability distribution function of f of t. This is the so essentially here's what I'd like you guys to do in the homework exercise that you do is that I want you to generate a first one a Poisson process and then a real spectrum. Okay, and the real spectrum you have a density function, probability density function is something like this. Okay. Now, of course, from here you can compute the distribution function that is f of tau by integrate this, right? This is density function, remember. Then you have that function, something like this. Once you have this, then use the mathematics there. Then you can produce this function. Okay, this function. So what I want you is that being able to generate it, then generate a real spectrum that is statistically is indifferent from the real spectrum activity. That is why we're doing this mathematics here. Okay. And then we're doing here. And I will say, spend a little bit of time to go through here. And this formula given to you, if you have energy, try to prove it. It doesn't take much to prove. You can prove mathematically. This is true. Okay. Now, is this part clear? Might not clear. So let me one more time. So idea is following. This is exactly homework I give it to you to do today. So I'll give you a real spectrum, n spikes here. I say build a mathematical model that can reproduce this spectrum again, forever, however you want it. But what you produce is statistically accurate. So what you produce is not exactly this one, point to point. But if you compute the interval histogram of what you produce, they will be the same interval histogram here. So statistically, they're equivalent. How you go through here to here, give you one spectrum. You take spectrum, calculate interval histogram first. Then use that formula to generate a new spectrum based on interval histogram. Start from a uniform distribution. Then once you have this, then you can compute continuously forever. Now, of course, this is inverse function. And then now mathematically, you may not be able, actually, you won't be able to do inverse function. If it's a Poisson process, inverse function is easy. If it's a gamma process, you cannot do inverse function mathematically. What do you do? Do it numerically. If you can't do it analytically, do it numerically. You can still do this. So that will require you to do this. Okay? What's happening now is that you will have a mathematical neuron, model of neuron, that is identical to the neuron you generate. This is an exercise I want to do. So once you go through here, and then you have full control of everything in that spike. From the simple to more complex measurement to a mathematical model. That is whole 9 yards. We would like to walk through. Okay. And finally, and this is part that some of you might need more time to understand, and I strongly advise everyone, including your especially friends who are not here, to spend time understand this and do this homework I give it to you independently. The homework I have to confess to you, this homework takes a lot of time to put together. I only make small changes from year to year. So if you make effort, you find it last year. But it's not worth it. And it's not quite the same. Okay. Start years ago, I kept giving homework the same thing. One year I said, I just want to be curious how many students really do their homework. So without telling my TA, I put a negative sign in one of the formula without telling anyone. And then without negative sign, the curve should go this way. So one homework on the TA. So when you guys look at homework, if you ever see a curve go that, if you see, then put a negative sign, the curve should go this way. I told my TA, so if you see a homework that goes this way, tell me no. Sure enough, not everyone. And most people did the work. There's a couple people in class, the curve continue to go this way. It can't be, because they didn't pay attention. That was just small trick. But what I'm saying, so don't assume what you got is the same as last year. But more importantly, more seriously, do that homework because it's really meant for you to understand this. That's what I meant, not a trick. And if you have questions, discuss with TAs and to fully understand. All right, see you, Mark.